going to draw the transfer characteristic of this network. So the voltage, the output voltage is V0. Switch color here. It's V0, and let's call this point A. So we wanted to sketch the transfer characteristic. Characteristic, which is we're gonna have the output over here and the input over there. So for the diode, the IV characteristic of the diode, it looks like this. So we are going to approximate, so it's something like that, but we are going to approximate with this brain, and this is the VD on. So in most cases it's equal to 0.7 volt. So this is the diode voltage, and this is the current to the diode. Call it ID. Now, so this is the resistor R across which we measure the output voltage. Now, so before we solve this, in this network we have an op-amp, operational amplifier, and diode. So for the operational amplifier, we have called this V plus, V minus, and this is the output. So the voltage here, VA, is the open loop gain, which is on a 10 thousandths, right? It's 10 to the 4, 10 to the 5, 10 to the 6 is big. So which is V plus minus V minus. So in open loop, the output of the voltage is the output of this open loop op-amp is the open loop gain times the difference between the voltage at the positive terminal and the voltage at the negative terminal. So because this op-amp will be power, I need external power, the voltage across the VA cannot exceed the rail voltages. So this will saturate, right? So VA will saturate depending on the sign of the output the difference between the positive voltage V plus and V minus. So when we look at the network that we see over here, so when VI is positive, then VA, right, based off the network that you see above. So based off this, so where we have the op-amp, and then we have the diode connected between A and V minus. And then we have a load resistance. which is called R, connected to ground. And the goal is to measure the voltage here. So when the input voltage VI is positive, okay, the diode start the circuit, not the diode, the circuit, okay, start operation. So and VI has to exceed some small voltage, right? So VI must exceed some small value, some small value that I'm gonna derive in a minute. Some small value. So which is given by what? So which is given by the VD on divided by the open loop gain. So when the circuit start operating when VI is positive, what really happens is that this point, that point VA, the voltage at that point VA is equal to VD on. Right, could replace the diode by that constant voltage VD on. So VD on now plus RID, because the current here I minus is 0 and I plus is 0. So when the diode conduct, then ID must be positive. So that means VA minus VD on must be bigger than 0. Now, what is VA? So we know that VA is equal to the A times V plus minus V minus. Okay, so when the network start operating, then VA V plus, right? Because the VI is connected to V plus, we'll have VA equal to A times V plus, right? Because V minus, right, which is connected to the output of the diode right before start conducting is 0. So then I will have a VA, which is A times V plus minus VD on must be positive. So that means V plus, which is the VI, will be equal to VD on over A. Now, so must be bigger than VD on. So this is the threshold, right? VD on minus VA is the threshold that VI must reach for the network to start operating. Now, when the circuit start operating, then we have VI bigger than VD on over VA over A, but A is so big that we can assume that when VI is bigger than 0, then the diode is on. So when the diode is on, the closed loop, the loop right? The negative feedback is closed, right? So then we have this scenario. So I'm gonna sketch it down here. So we have that scenario. This will be the diode. This is VA, and that will be V0, right? The voltage here will be V0, and that's the resistor, and this is the VI. So then V0 will be equal to VI, right? Because when the circuit start operating, VI, right, when we have a negative feedback, VI would tend to be equal to V plus, right? Will tend to be equal to V minus, right? Meaning that V plus minus V minus must almost equal to 0. Okay, so that when we multiply by a constant gain, the A, right, that gain will be a finite number, small finite number. Okay, so when VI is positive, that's the condition. And then let's look at when VI is negative. So when VI is negative, then VA, which is A times V plus minus V minus. Okay, so it will be negative. So when it's negative, the diode will be off. The diode does not conduct, so the diode is off. So when the diode is off, I break the loop. So the network is the op-amp is going to be in open loop state, right? So open loop state, and then there's no current to the resistor, right? So then there is no current to the resistor. So V0 will be equal to 0. So now let's summarize. So V0 will be equal to VI when VI is positive, and then it's equal to 0 when VI is negative. Now, so we can sketch the transfer characteristic. So we have VI here, and V0 here, and the slope is 1. Okay, slope is 1. So that's the transfer characteristic. Okay, so the voltage will be, the transfer characteristic looks like this, with slope equal to 1. Now let's solve another circuit. So this is going to be the second example of super diode. So I'll call it example 2. So as we saw earlier, so let's call this R, this is R, this is the load resistance, RL, and we want to measure the voltage across this load, which we call V0. So now when Vi is positive, the voltage at this point A, okay, so anytime we deal with op-amp circuit, we need to keep in mind and look for what happened at that point A. So we know that the voltage VA, so assuming the network is about to start working, the op-amp and the network wasn't, the diode wasn't conducting, so VA will be equal to A, the open loop gain A, so V plus minus V minus. Okay, so right before the diode start conducting, so VA will be equal to A times V plus. So well, I would say VA is positive. So when VA is positive and goes above some threshold, then the diode will conduct. So when the diode is on, then we can replace it by a constant voltage source. So we have this R connected to the negative terminal of the diode, and the plus is connected to the input voltage Vi, and we have this resistor R that goes into here, and we have that diode and VD on, as we said above. So characteristic of the diode, which is sort of this, we make an approximation, and that's what we call VD on when the diode is on. And then the current to the diode at that point will be positive. And then this is connected to the load resistant to ground. Now, so when the diode is on, the condition is that the diode current must be positive. So we're going to use this condition, and mostly, as if you have been watching the videos, we use this condition to find the condition under which the diode will turn on, and the condition under which that relates to the input voltage for the diode to turn off. So when the network start working, meaning the diode is on, we know that the V plus will tend to be equal to V minus. V plus equal to V minus, so the voltage here will be equal to Vi as well. So the current here, I, will be the same current here, because there's no current flowing to the op-amp. So this is 0 amps. So then that current will be 0 minus Vi over R will be equal to Vi minus V0. So V0 over R. So then what do we have? We have Vi, so we could just cancel with we can just simplify the R. So that means Vi equal to V0. Equal to V0. So this current, which is 0 minus that, and 0 minus divided by R. So VI equal to V0, no, 2VI, if I'm not mistaken. So let me bring this. So minus VI equal to minus V0. So V0 equal to 2VI. Okay, so when the diode is on, this is the output voltage. Now, if I wanted to check the conditions, I could just write the fact that the KCL at this node, and then find the current through the load, which is equal to the feedback current plus the diode current equal to the current going through the load. So then the voltage, right, at this point A, as I indicated, I have to keep that in mind. This is the point A. So VA will be equal to VD on plus V0. So which is VD on plus 2VI. So whatever VI is, like if I say positive voltage when the diode conduct, then VA will be equal to VD on, which is mostly 0.7 plus 2VI. Okay, so now when the input voltage, so this is the other condition. So when VI is negative, I mean the voltage at point A will tend to be negative, right? So VA, right, will be negative. So this is let me copy this down there. Maybe when we have it in front of us, we'll see. So the voltage here, this voltage VA, right? So VA is that voltage. So let me point to it. This voltage VA will be negative, right? Because right before, when it's negative, when VA is negative, we have VA, which is A, V plus minus V minus. So the negative terminal right before it conduct, this, because V plus, right, the voltage, this is connected to VI, so this will be negative. Okay, so when VA is negative, the diode will be off. So diode is off. So when the diode is off, there's no current flowing there. So the loop is open. So when the loop is open, there is no current. So there is no current flowing through the load. Right through the load. So V0 will be equal to 0. When you use Ohm's law, the current there is 0. So V0 equal to 0. So what we have is, when we put them together, so V0 is equal to 2VI yeah, 2vi. When vi is positive, and then it's equal to 0 when vi is negative. So you can draw the transfer characteristic for this network as well. So vi is here, v0 is there, so the slope here is going to be steep. So slope is 2. Okay, so that's the transfer characteristic for this network. So to recap, so when diode on vi or v0 equal to vi, the condition that vi is positive, and va is equal to vd on plus v0, which is vd on plus v2vi. Now when the diode is off, then vi, so when vi is less than 0, so diode is off, and v0 equal to 0.